Yeah, thanks, Ryan. Is that okay? That's okay?
That's perfect.
All going? Excellent. Okay, first off, I'd like to acknowledge the Wajik people of the Noongar Nation as the traditional custodians of the country and its waters, and that Ark, from where I'm speaking, stands on Noongar country, and I'd like to pay our respects to Noongar elders, past, present and emerging. So, this talk is a, I thought it would be useful with COVID, even 5 months in, with more people working remotely, to draw some attention to some software that anyone can download and use and maybe help them in their day-to-day. So the talk is a slightly expanded version of the work that I presented in Sydney at the first AEGC conference in 2018. It's slightly expanded because 20-minute conference talks can only contain so much information, and we have the time. It's also for at least one of the audience, a slightly expanded version of the talk I gave for the ASCG about a month ago. That talk is currently on the ASCG's YouTube channel. The ASCG, of course, stands for the Australian Society of Exploration Geophysicists. So, acknowledgements proper. I'd like to acknowledge input from CSIRO colleagues, in particular EMIT, Kim Franken and Ron Palmer. I'd like to acknowledge the industry sponsors for supporting the six three-ish year projects that culminated in these codes. And I'd like to thank Joe Kutza, my co-author, who with AMIRA International and now with Industry C2I, was responsible for liaising between many industry partners and CSIRO's electromagnetic modelling group. And the final acknowledgement is, of course, CSIRO's electromagnetic modelling group. In particular, Art Raish and Fred Sujing, both of whom are now retired, but also others such as Neil Flood, Jean-Pierre Jean and Glenn Wilson, who made substantial contributions to the code base. So I'm going to talk about the series of projects. I'm going to talk about the codes, what they do and how well they do it, and then I'm going to talk about some open source projects, and I'm going to offer some thoughts in that space. But first, I'm going to talk a little about electromagnetics and modelling in order to provide some context. So, why use electromagnetics? Well, one reason to use electromagnetics is the large variation in electrical resistivity, or its inverse, electrical conductivity, in typical earth materials. Incidentally, I'm probably going to alternate between electrical conductivity and electrical resistivity throughout the talk, so I'll apologise if that bothers you. Moving on, so the image on the right, which is taken from Palaki's chapter in Volume 1 of Nabigion's Bible, the First Testament, if you like, shows some variation over several decades. And over those 7 decades, there's a reasonable degree of separation between materials. For example, generally, based on resistivity alone, we can differentiate between massive sulfides, which tend to be conductive, and their host rocks, which tend to be resistive. And we can do the same trick with groundwater. So we can differentiate between saline groundwater, which tends to be conductive, and freshwater, which tends to be resistive. So another reason to use EM is that we can use an active source. So although we can employ passive techniques such as MT, which is nascent, active sources offer control over noise ratios and polarization, and we can interpret the results based on a particular primary field source vector. So the previous slide mentioned Maxwell's equations. 3 of these are critical. First one is Faraday's law, which says that time-varying magnetic fields induce electrical fields in conductors. Ohm's law says that the current generated by those fields is proportional to electrical resistivity. And Ampere's law says that those currents in turn generate a magnetic field. So typically, EM prospecting measures the magnetic fields, the currents induced to flow in the ground by a time-varying current, typically flowing in the transmitter. The difference in the measurements are related to non-linear variations in the ground's electrical resistivity. So why do we need modelling software? Well, unfortunately, the measurements are related to the underlying conductivity variations. They're also related to variations in current. They're related to variations in transmitter height, in receiver position, orientation, survey direction, variations in culture, power lines, etc. And all of these are non-linear to varying degrees. So the upshot is that we cannot interpret directly from measurements. So the example data set on the right shows a line from GA's Patterson survey in 2010. So we see a whole bunch of wiggles, inline component field, which is the field going from right to left on the top. The second slide down is the variation in vertical component, which is the component looking downwards into the Earth. And the lower three slides show variation in altitude, ground clearance, variation in transmitter orientation, which is pitch and roll. And we can also see the variation in distance from between the transmitter and receiver. So some of the bumps we can see correlate in the top two panels correlate between two bumps on the lower three panels, but some of them don't. Which brings us to geophysical modelling. So geophysical modelling is a large topic, and I don't propose to talk about it in any great detail, merely to provide some context. So I'm going to brush over the surface and draw heavily from slides presented by Stephen Constable in his 2018 SEG Distinguished Lecturer at World Tour. So geophysical modelling can be seen as a process of recovering the model of the Earth from measurements. This is very much an inversion-centric point of view. So using EM, we're going to characterise the Earth as a distribution of electrical resistivity. And we can note from the diagram here that there's no particular requirement on the structure of the Earth, nor how we're going to find it. Geophysical inversion is very much a philosophy. So we haven't spoken about how we're going to parameterise the Earth, our model. So in general, given model parameters M and independent variables X, such as frequencies, locations, source moment, disposition, and some functional F, we can predict the response D. And our functional F varies from simple to complex, from fast to slow, and from rarely applied to commonly applied through 1D all the way to 3D. Inverse modelling is just the process of recovering a model from the data. There are usually three ways to proceed. An analytic solution. More commonly, though, we use deterministic algorithms such as Stokes descent and conjugate gradients, which seek a model based on the relationship between changing model parameters and data. And the other commonly applied technique is stochastic algorithms such as MCMC or Bayesian parametric bootstrap, which sample solution space and model parameters are inferred based on their statistics. So in keeping all this in mind, we need to be aware that we're unlikely to accurately parameterize the Earth. And this sounds a little pessimistic, and in some sense it is. Nevertheless, physics-based models are a powerful mechanism through which we can understand the Earth. So we should look at the Earth and some of the models we might use to try and understand it. And these are the functional F from the previous two slides. So it might be useful to illustrate this in a high-level context. I'm going to base this section on a general model of the regolith, which includes some hydrogeology, which is taken from the Queen's CSIRO Mineral Exploration Program region in New South Wales. So I've highlighted two sections in the geology here, which may be amenable to modelling using 1D models. So conductivity varies only in the vertical direction. And these are sections here and also here. So these models are very simplistic, but they're also quite effective, and they're easy to use and pretty quick. The next abstraction is 2D, and these allow variation vertically as well as laterally, typically in the direction of the profile. And 2D models, because of their assumptions, which are that topography and geology are infinitely long, are used therefore to model long structures. So in an EM context, long is taken to be larger than the footprint of the EM system, long enough that distal variation in structure has no practical influence on EM response. The final level of abstraction is 3D models. So in a most general form, making a variation in physical property in any direction. This means that to varying degrees, we can easily model the full diagram of the regolith with high geology. Another type of 3D model is somewhat simpler, and these are general 3D geometric objects such as a prism or a plate which is embedded in the earth. So, with some context established, it's probably worthwhile talking about the industry codes. So, after 6 successful industry-funded AMIRA projects, the project leaders at the time were diminished. And projects of its final sponsors suggested that codes could be released after 2-year embargo, and therefore the codes were released to the public on January 1, 2009. So these codes were designed to model external prospecting systems and survey configurations. The versatile, you can model airborne, fixed, and local community systems. You can model ground dipole, youth and wire transmitters. You can model ground dipole, youth and wire systems. All of them use whole resistivity model, the complex conductivity model. And the inverse algorithm, where the such as there, includes the jump and close off SVD approach from 1975. So, portability. They use ANSI standard F95 sources and without any local dependencies. So what that means is G4tran -03 program name gets you a fairly well optimized A.out with no compilation warnings that will run very quickly with very few surprises. One of the consequences of no likely dependencies is therefore that they're listed record. You can incorporate a multi-processing capability and that's what I.O. is flat ASCII for portability and ease of use. So what are the models? Well, here's the models. Beowulf class on the left is essentially 1D. The LeroiAir and Marco classes are 3D geometric bodies which are embedded in a 1D Earth. The Samaya class is essentially a half-space with heterogeneity. And the final ones are the Loki and Arjun classes, which model 3D and 2D structures respectively. These are finite element programs. So, symmetrics. Marco has the largest code base, and these are lines of code the left, so there's no comments in that. And most of the size of the Loki distribution here comes from examples. And incidentally, all the codes are provided with examples, which cover most of what you probably want to do. So, it's conventional with codes to talk about their accuracy. However, comparison between different codes isn't really that simple. And the reason is that different approximations can imply different physics. So we have to cater for different limitations in the codes themselves. For example, some codes don't account for strike angle, because of the Marco and the Arjun classes. Some codes don't account for dip angles, that's the Marco class. Some codes only involve half spaces, which is the Samaya class. Discretization has a strong influence on what can be run, which kind of limits the effectiveness of the Arjun and Loki classes. And discretization can have a major influence on the model results, again, Arjun and Loki classes. Nevertheless, there is some common ground between the codes. So what we're going to do is compare some program outputs and as profiles and as decays at selected stations. So the first model is a thin target and a conductive regolith. So the model we're going to base this section on is a 50 metre thick regolith over a 1,000 nanometre basement. We're going to vary regolith resistivity. A single vertical target is present in all of the models, and that target is has a depth top of 75 metres, or 25 metres below the bottom of the regolith. The target has a nominal thickness of 10 metres and at a resistivity of 0.01 metres. It has a conductance, which is the conductivity of its product, 100 seconds. So all of these figures will have the conductivity contrasts down here. So over the next few slides, I'm going to vary the resistivity of the regolith, which is this orange section. So for the data on screen, a thin target and a conductive regolith, we don't expect any target signature, simply because of the conductive regolith. But we might also note that we have a fairly good agreement between all the codes. The limited spatial extent of load is primarily so we have the memory available to run the model. We have Arjuna profiles in green, Marco profiles in red, LeroiAir profiles in blue and grey, which is our LEI, which without the target in grey. So let's decrease the conductivity of the regolith by a factor of 10. When we do so, we can see a little more of the target signature. We still have reasonably good agreement between the codes. Loki's noisy. There are reasons for that, but in general, we have some fairly good agreement between all those codes. Let's increase the resistivity of the regolith by another factor of 10, and we can see a few more differences in later times, especially around the centre of the model. More differences here. Final model is actually a target in a half-space, 1,000 nanometre half-space. This is actually a fairly difficult model for some of these programs to model accurately, simply because of the large contrast and the large contrast in conductivity. Nevertheless, we're actually getting some fairly good agreement between these codes. And we can see that by looking at decays. So starting far on the left of the profile at minus 2000, I'm comparing everything. The Arjuna response here in green is simply a manifestation of the 2.5D model of Arjuna, which is an infinitely long target. So we expect Arjuna air responses to dominate at later times. So let's move closer to the centre of the model. And again, pretty good agreement. Still closer. Still closer. We can see now Arjuna is really modelling a 2D structure, but otherwise we have reasonable agreement that we expect. Marco's broken down because of the very large conductivity contrast. Marco's nominally rated for a 300 to 1 conductivity contrast, and we're exceeding that by a significant margin here. Directly over the target, these are the results. I mentioned inversion. So we can also invert these data sets, and I've done so here using the code Airbeo. So these are typical individual stations plotted adjacent in a stitched section. So essentially the regolith in the background have been recovered reasonably well. We expect poor results in the vicinity of the target. And we can see that by looking in detail at the model diagnostics at particular stations. So we have minus 2000, minus 1000 east, minus 500, I think, and it gets close to the target here. Incidentally, one of the advantages of the open source code is that you can easily modify the output to produce these things. So I show the data resolution matrix here as well as the model resolution matrix. And all of these provide reasons as to why the inversion might be failing. The fundamental reason the inversion produces fairly poor results over the center of the target is, of course, that we're using an inappropriate model. It's just unreasonable to expect a thin vertical target to be accurately modelled using a layered Earth. And you might be surprised that when we actually use an appropriate model and invert for a thin target under a conductive regolith, that we don't do too badly. So these are this is an example of that inversion where error is reasonably okay, and all of the parameters are recovered reasonably well. So, in summary, all of the codes have limitations. Marco Air has conductivity contrasts limitations. LeroiAir has limitations in terms of discretization, and Arjun GUI has limitations because it models infinitely long structures, and that can bite you in all sorts of interesting ways. We see differences in amplitudes between near sharp conductivity contrasts, but otherwise, character and anomaly is fairly similar. We get reasonably good matches between all the codes. And we've also seen examples of codes that have been used to invert data that are just inappropriate. Nevertheless, the good matches in overall, despite different modelling methods and the approximations, suggest a fairly high level of accuracy in these codes. Which brings us to 10 years in the wild. So as I mentioned, these talks have been in the public domain for over 10 years. And it's interesting to see how they've been used. Has the release been successful, at least in some sense? So, unfortunately, there doesn't appear to be any agreement on how to assess project success. There have been a couple of studies that I could find, and so we're going to use these, some of these criteria to assess the success of a 223 code release. But before we start, it's probably worthwhile noticing that one of these studies, Schweik's in 2013, considered about 15% of just under 11,000 project releases successful. So out of those roughly 11,000, only 1,500 projects were considered successful. So let's proceed. I've mentioned Schweik's study, but another one's Geophysical et al.'s. And these are the criterion they use. Geophysical et al. Use user interest, project activity, effectiveness, efficiency and quality, and Schweik assessed project success on the initiation and essentially how well it does after that, whether it was abandoned, how well it grows, and whether that growth can be at all charted. In a 223 context, this is how they look. So there's user interest, the projects have been effective, the project quality, I hope you'll agree from the previous few slides, has been high. Nevertheless, although the project was released, we're probably going to have to say things are indeterminate in growth. And one of the reasons for that is that there is no guarantee that the downloaded codes are used. And secondly, there is no guarantee that any use of the downloaded codes is reported. So codes can be downloaded and they can be used by students, but not written up. Codes can be downloaded and used internally by companies, but those results never see the light of day. They're entirely reasonable caveats, I think. Nevertheless, we can trawl the literature, and when we do, we can find this, these sort of references. So essentially, 72 papers and conference talks since about 2008 suggest there's probably some interest in the codes. We can also look at a Sourceforge downloads page, and again, interest from all over the world. I still don't know what this peak here is. It is from China, but I don't know why. Maybe we'll never know. So there has been some uptake, and it's interesting to see what that uptake looks like. So that's the subject of this next section of the talk. On one hand, there's some commercial uptake. You can buy the codes from EMIT in Western Australia, as part of the Maxwell package. And my experience is that they work pretty seamlessly. You can describe a model, you can import the results for direct comparison with your field data. Intrepid run a 2.5D service, and Geotech used some of the codes as part of their airborne IP processing. There's also been some uptake by government and academia from the Finnish Geological Survey, and also within CSIRO. So I'm going to run through some of these applications next. The first one's Geotech's airborne IP processing system, from 2016. So Quantum Lego used the Airbeo kernel, but they've thrown away the SVD decomposition and use a Nelda-Mead simplex minimization instead. And here they show examples of inverting VTEM data for IP effects. Another example is from the Finnish Geological Survey. So these guys have wrapped Arjun GUI in what looks to be a fairly good-looking GUI. It appears well thought out and designed to ease the process of inverting data from a 2.5D Earth, but beyond that I can't really comment since I don't use Windows. But if you do, and this looks interesting at all, I'd certainly commend this for further investigation. Closer to home, one of my colleagues, Aaron Davis, isolated the LEI Earth computations from Leroy, and he drives those computations from MATLAB towards an reversible jump Monte Carlo Markov chain Monte Carlo scheme for interface definition. And this is around water, knowing Aaron. So if this interests you, I can suggest you contact Aaron for more details. Another application is the probabilistic inversion for spatially coherent interfaces. So here I show the paleo channel around the Kintyre uranium deposit. Here's the Airbeo channel, and here's the Kintyre uranium deposit. And these are taken from GA's Tempest Patterson Tempest dataset from 2012. This shows a flavour of the uncertainty along the, in depth rather, along the top of the paleo channel around this northing here. Hauser et al. Used the Airbeo kernel here. More works around objective risk calculations. So here, Hauser's driven the groundwater modelling program, ModFlow, directly using surfaces from the airborne, from the Bayesian parametric bootstrap. And they use those surfaces to assess the uncertainty in the volume of available water based on structural uncertainty. So what that means is you can advise sustainable pumping rates in particular locations from a modelling study. So in a nutshell, they've used the surfaces here to advise the uncertainty here, use that to advise the groundwater program, and from that they can determine the optimal pumping rates. And the final application I'm going to talk about is the inversion of the probabilistic basement conductors, which has been described by Hazard et al. In 2016. So here we're using Airbeo in conjunction with LeroiAir for the discrete target to invert the there's geotech data from Walford Creek to determine the most likely conductor. And this, so the panel here is Idealised results, and the panel here is results from Jim McNair's paper. And there's some fairly reasonable correlation between the two. Incidentally, it's worthwhile noting here the way that depth of investigation neatly falls out of the Bayesian parametric bootstrap. As you'd expect, the probability decreases with increasing depth, and that's shown fairly well here. So, to conclude, some of the codes, but not all of them, are in use by industry and academia, and indeed some have been further developed by industry and academia. So in that sense, a compelling case could be made that the 223 code release has been successful. However, we'd also have to say that the codes have yet to transition from a collection of codes to a proper open source project. And I'd like to talk about that a bit further. So it's natural, I guess, to ask how those codes might progress from a simple code dump to a bona fide project. And to me, that comes down to project definition. What does industry and academia want from these codes? Schweik, in addition, offers project administration, so it needs an active encouragement by some project managers, milestones, in order to foster a virtuous circle where developers are essentially assisting their competitors. Clearly defined licensing helps, as does financing, and I probably need to talk a bit about that some more. So, despite being freely available, these open source codes aren't actually free, and it might help to think about how you pay for them. So, investigating bugs isn't free, unless you do it yourself, which costs you time. You need to, the bugs need to be tracked down. Updates aren't guaranteed. However, in the sense that the codes themselves cost very little to run, to study, or to download, they are actually free. But much like free beer, it's fine if you're happy with a single beer. Otherwise, you need to buy some more or discover the wonders of home brewing. So 5 successful open business models are listed here. Classic models, Red Hats, of course. So use the software for free, but you want it in support, it's going to cost. Another one's hosting model. So your data, our hardware, our software. The third one's a restricted licensing. So the Q2 development framework has different licensing options depending on the user. One user path has the hobbyist, in which case you get the full GUI framework for nothing. The other development path is commercial application, in which case you pay accordingly. There are hybrid models. OpenDetect has a open core with plugins cost, and there's a four which is a combination of quite a few. So, assuming you're still interested, there is but a small hoop to jump through to acquire these codes, and that's this is the fine print that you'll be ticking. But the gist of it is, use the codes how you want, but acknowledge who wrote them and who provided them. And the answers to those questions are CSIRO and AMIRA International. The second one is that the codes don't use any of the 200-odd open source licenses. And the third one is that despite lots and lots of testing, the codes might contain bugs. In fact, they probably do. No one's guaranteed to fix them or to tell you what they are. All codes have limitations, and some of the limitations aren't bugs. Following this QR code, it will get you those codes. So that's my talk, and I'm happy to entertain any questions.
Okay, thank you, Dave. We haven't had any questions come through. We've had a few technical difficulties with the sound throughout this presentation, but if anyone would like to come off mute and ask Dave a question, please feel free to do so now.